Good afternoon, everybody. We're going to get started in a couple of minutes. So if you can work your way in and find a seat, that would be great. All right, I'm going to channel my inner Mamduh Sifri, and I'm not quite as bold as Mamduh, but if we could get everybody to come in and find a seat. Welcome everybody to the 2022 Informal Nutrition Symposium, the first live symposium after 2 years of online. In the interest of keeping our program on track, I'm not going to spend a lot of time introducing the symposium. Rosalina will be our first speaker, and she'll do that. I did want to take a moment to acknowledge the planning committee for the Informal Nutrition Symposium, and that is Todd Applegate from the University of Georgia, Rosalina from the University of Maryland, Mamduh Sifri, who unfortunately is not able to be with us today. But Mamduh was, of course, heavily involved from Sifri Solutions, and myself, Doug Korver, from the University of Alberta. So with that, Rosalina, if you would come up. I'll just point out while Rosalina is coming up that we're keeping this informal, and we won't have long introductions for each of our speakers, so we'll just introduce them and their affiliations, and they can get started.
So welcome, everyone. Thank you for spending your afternoon. I hope most of you stay till the end because we have an amazing set of speakers. We planned this, and every single speaker that we tagged said yes. That doesn't occur every time that they can come and be here. So they'll be thanked at the end, but I want to thank them for being here. I had some slides that I may not even use, simply to give them the time that they deserve because they're the main event. But we wanted to do something to make sure we make the point that when we're feeding animals and we're managing animals, we need to be holistic in our approach. It's not a static requirement for maximum growth at such an age. It's more of a dynamic system. So, well, I may use a few. So ingredient selection, we have to consider ingredient selection, quality, a dynamic nutrient content, use commercially, and it's surprising how many commercial companies are not there yet, and real-time nutrient content use in formulation. And we'll see definitions of real-time by one of our speakers. Then feed production. That's one of the areas where I see the most errors in the field in terms of what we formulate is not necessarily what the animal actually eats, and that is a huge concern because it throws everything for a loop. And then we have systems where we have pellet particle size of the meal. We have pellet durability at the feed mill, and then you have something like this that the bird actually sees that has nothing to do with the pellet quality that we saw at the feed mill. We end up with problems, I know this is here, with problems where we're formulating, where we're formulating in this black line. This is what we should be analyzing. This is with phytase and calcium, and this is what actually the average is. So this is not abnormal. Most companies will say they can actually mix correctly, and it's amazing with certain nutrients that doesn't really happen. And then on a requirement standpoint, we've tended to look a lot of the time at static requirements, and we'll be hearing about the need for a more dynamic system where you bring in what is it that we're selling, what is it that we're producing, and what is our optimal economic production of what we are actually selling, not the requirement for maximum growth, which sometimes may be optimal economically, but most of the time it probably is not. So without further ado, our first presenter is Dr. Klasing from University of California, Davis. Well, he's retired now, so we're happy to see him here.
Yeah, I went through it before.
Well, thanks, and sorry for that. I've been giving presentations for 40 years, and I still don't know how to put the slides to work. I'm just going to give a real short presentation on the historical aspects of nutrient requirements in poultry. Some of this is based on some research I've been doing as part of a National Academy of Sciences committee that's supposedly redoing the nutrient requirements of poultry. For that committee, we've kind of looked at what's gone on in the past. But the first report that came out that had a serious attempt to estimate nutrient requirements of chickens and to some extent turkeys was in 1944. That was the first publication from that National Academy of Sciences series. They actually, even though it was called nutrient requirements, they actually didn't use the word requirements, except in the title. They called them nutrient allowances because they didn't think the data was good enough to call them requirements. Because most of the research was based on experiments that were designed to determine whether or not a potential nutrient was actually required. Not what the requirement was, but was it required? And so most of the endpoints they had were things like pathology, death, not the type of endpoints that we would typically use in requirement studies. And so since they didn't feel comfortable, they had a pretty large margin of safety. They didn't exactly explain what it was. They just said that they used a margin of safety dependent on how confident they were in the data. They looked at protein, 5 vitamins, and 5 minerals. The next one came out in 1954. There were a couple updates, but they weren't much. 54, there was a major update. By that time, almost 3/4 of the nutrients were known to be required that we now know are required for poultry. There were experiments that were designed specifically to look at requirements. In other words, they had multiple levels around the optimum for growth. And so they called them nutrient requirements, pulled out the margin of safety, and said that the user can put in their own margin of safety if they don't trust us. They did protein, 10 vitamins, 7 minerals, and they did doing 2 periods, starter and growers, but not for layers. So there was just a little bit of mention of egg production. So that was 54. I was born in 55, so that's about when I was coming out to start thinking about these things. The next major update was in 66. By that time, there had been experiments that were clearly designed for requirements for most of the known nutrients. And in their report, they had protein, 13 vitamins, and 10 minerals, but no amino acids, not even methionine. And they didn't differentiate between chicken types of broilers and layers. It was just growing chickens. It wasn't until 1984 that they fully differentiated and had sections on broilers and layers, pullets, turkeys, and then those experiments were based on even better experimental designs, and I'll get into some of the aspects of those experimental designs in just a second. The last one was 1994, and that was a large update, increased the number of pages by fourfold, and the update that we're working on now, which hopefully will get done this summer, is probably going to be another fourfold increase in numbers of pages. Whether it's an increase in understanding, I don't know, but it's an increase in volume, that's for sure. So some of the refinements that have occurred over the last 25 years or so, one of the big ones was use of a common basal diet. Back in the 50s and most of the 60s, there wasn't a common basal diet for most experiments. They just mixed different levels of corn and soybeans to get different levels of some of the nutrients. But over time, it became understood that a common basal diet, to which is added a more purified form of the nutrient under consideration, was the way to go. Also, the number of experimental treatments was greatly increased so that the dose response, both below the maximum growth rate or feed efficiency, could be mapped out, as well as at the plateau. There was a lot of work looking at appropriate endpoints, not just growth or feed efficiency, but also body composition or other functional characteristics. And then also the idea of actually measuring the amount of nutrients that you're looking at in the diets that are being used in the experiment was introduced. First time I saw that done was in 1969 in a paper. Before that, if it was formulated to be that, that's what it was. And then there was, especially in the last 20 years, a big development in appropriate statistical methods for measuring the dose response and determining where the optimum is, instead of simply a broken line type of approach, because there's no reason to think that all responses to all nutrients are linear on the way up and flat once you get there. So I think the statistical appreciation has also been a major development. And with that, I'm going to turn it over to Dr. Ferket.
Thank you, Kirk. Well, you know, estimating requirements has really, as Kirk pointed out, has improved incrementally. But the expense and time that's involved with that is a major constraint. And for those of you who formulate a diet, the more constraints you have, the more infeasible things become. And so that results in decreased output. And so really it's time for a transition to maybe a more robust approach. You know, if we look at chicken production over the past many years, Kirk says he was born in 1955, I was born in 1957, and there back in 1957, to get a 42-day-old broiler was weighing just a half a kilo and 2.35. Took more than 112 days. If you project now, we just finished some experiments at NC State. 2020, we can get easily 3,500 gram 42-year-old bird with a feed conversion of 1.4 in 27 days. And if we project in that same about 50 gram weight for age for a 42-year-old bird advancement every year, that's a 1% improvement. We should easily, by 2030, get a 4-kilo bird within 23 days. Absolutely phenomenal. Will we do that? I don't know, because that really depends on economic pressures as well as social, etc. If we look at turkeys, same sort of linear progression. Way back before, in the early days, I used to do an annual survey of the turkey industry and stopped at about 2005 But we've did some research recently and together with Dr. Jesse Grimes, and we've got some statistics there on performance of birds. And again, you can see a fairly good linear response, and you can see these annual improvements in terms of weight is about 300 grams a year. Quite phenomenal for male turkeys. It looks like they're starting to plateau off now a little bit, but nonetheless, there is this progression towards faster growth, and that's purely because of economics. So when we look at the nutrient requirements for poultry, we know that nutrient requirements changes every day, and our dietary restrictions or requirements are expressed as a concentration in the diet in some way, and then there are individual variations within a flock, so you have to consider that. And there are needs for these nutrients related to maintenance, growth, and reproductive outputs. And there are many factors that influence that, especially feed intake. It's the one thing. We think feed intake we know, but we don't know. And so that creates issues. Either there are factors like intrinsic factors like infections and non-infectious diseases, and then there are extrinsic things such as the environment, etc. So there's been a number of publications. Starting off, I have here, this is the 1994, but we have other references, feedstuffs. There are breeders come out with recommendations. We have the National Animal Nutrition Program that provides information, and then there are some models out there. And we have Dr. Rob Gous here, who will address you later, but he's one of the pioneers in modeling together with Jerry Emmons and Fisher. And if we look at just the 1994, this is the lysine requirement per, and I'm using turkeys because I like working with them. It's the lysine requirements simulated for the growth performance of a turkey back in 1994. And then if I took the 1994 NRC recommendations and their feed intake, this is kind of like the variation you will see with how those birds are actually getting lysine, consuming. So you can see we might be fairly well early on, but things got really hairy later. And this might be one of the reasons why right around this period, from about 10 to 16 weeks of age, why we often see a lot of problems with turkeys. So that gives us an opportunity for maybe getting a better handle on things, more predictive, and that brings us into this biological simulation models. There are empirical models, which takes in information in sort of a black box where it's based on just the proportion of body protein and lipid, can determine certain outputs. Or we have a mechanistic model, which actually is based on ATP generation, and it's a little bit more mechanistic in a sense that we know where this energy comes from and how it's distributed, and it can come up with a similar idea, but none of them really becomes very practical. So one of the things that estimating nutrient requirements using these computational models in poultry is the first fundamental thing is to simulate body weight, and that helps us estimate energy requirement, and from that, feed intake can calculate, and that's based on some nice research by Emmons, and Dr. Gous was a part of that as well. Then there's the biological models, and they can impute these desired feed intake. It's not necessarily the real feed intake, but then from there you can estimate the nutrient requirements based on the genetic potential for lipid and protein deposition. So if you can forecast that, you can come back and estimate that. And then you can simulate these feed intakes. Usually they differ, as I point out, from the observed values, and that depends on a number of factors I've already covered. So here's an example of some work done by Ye et al. In 1990, where they looked at unfeed restricted broilers up to 175. And if you kind of look, the black dots are the observed values using the Gompertz curve. Here's the equation. And in general, if you step back, it looks pretty well, except for towards the end where these big broilers couldn't stand up or lay eggs, right? But there's still, if you were to zoom in, it's still not exactly on target, but relatively good. But in reality, there are limitations to this Gompertz function in estimating growth and therefore nutrient requirements, because it only describes a single phase of unrestricted growth. And poultry actually grow in multiple phases, just as Kwazulu and Zudoff showed recently. And there are models now that can be used to estimate that, although sometimes their parameters are a little bit more difficult to understand. They do get us closer to simulating that growth. So as Dr. Zudoff nicely presented in his recent paper, and he was quoting George Box, and when I seen this, I thought, that's perfect. All models are wrong, folks, but some are useful. And computational models are well suited for discovery learning. And it gives us an opportunity now to not only develop hypotheses, but then ask questions and then do research to answer the model questions, so that you have an opportunity to develop models, readjust them, simulate, calculate back. And that brings us to this future of innovation, I think, in the poultry industry and indeed the entire world. It's technology. We have precision technologies available, data management resources, things with data analytics, new tools, meta-analysis, machine learning. All of these components can be now used to optimize some of these simulation models. So meta-analysis can be used to scan all of the published data and then perhaps identify complex nutrients. So Dr. Michael Kidd did this as an example for branched-chain amino acids. He peer-reviewed, it took 17 different peer-reviewed publications using the COB, and was able then to come up with a requirement based on that. Now, you and I couldn't do that, but a machine could do that, right, Mike? So there's an opportunity for us. Then there are machine learning opportunities where we can then take, which are very efficient and rapid and computational means to optimize nutritional programs in commercial production scenarios. You can data mine what is collected, optimize these models using everything from integrated sensors and geo mapping data and things like that to do so. So machine learning is a new opportunity for us. And we can take all the complexities that may be involved in poultry production, indeed even what happens in a particular house, using machine learning to optimize and mine that data, and then use different machine learning techniques and tools to actually develop new models as well, and to optimize and to disclose what things that we have missed in the past with just traditional empirical studies. So these machine learning devices can teach computers to learn without explicitly programming them for it. And they can solve problems without programming the machine and telling them what to do. So here's an example, one of my most recent PhD students, Victor Carvalho, did. And the question about coming up with a nutrient requirement in a feed to be formulated is always dependent upon getting a decent feed intake number. And so it's the real feed intake of broilers that we were trying to get after. So you need that number to determine the nutrient composition specifications. You can then come up with a daily requirement, but to actually formulate a diet requires knowledge of this. So his approach was to take the daily standardized ileal digestibility of lysine that's required to meet a genetic potential for growth. And here he has used that lysine equation for that's mapping using weight as the main parameter. And then come back and saying, well, feed intake times that lysine tells you how much lysine is used. And then from that, what's required gives you the wasted. And then using that machine learning target attribute, you can now use that real feed intake, and then taking all of the data that's being collected in the house gets you closer to what the birds are really eating but also disclose, hey, these guys are eating too much feed, check out, there's some wastage. And that'll give us this feedback mechanisms to optimize what that feeding program is. So the take-out message here for our presentation today with Kirk, a historical approach to estimating nutrient requirements have limited feasibility to accommodate the diversity of genetics, management, and output objectives that we have today. And these computational technologies offers a means to quickly determine these nutrient requirements suitable for different applications and reveal knowledge gaps and also generate hypotheses as well. And I think the poultry nutritionists for tomorrow will not only need to know nutrition and metabolism like we all have known, but they've got to be skilled data analytics and simulation modelers as well. So really we have an opportunity of using precision technologies to optimize these nutritional programs, and these will grow exponentially. And this is very important, especially as we enter in this new interest of life cycle sustainability assessment models. That's going to become a globally accepted way of looking at things, and the only way to achieve that is to start looking at our nutrition programs as modelers in that case so that we can project the impact of our programs. Thank you.
All right, thank you very much, Peter and Kirk. We will have an opportunity for questions at the end of the session. Just a reminder that PSA policy is not to allow for pictures being taken of presentations, so if anybody is doing that, I'd appreciate that you refrain from doing so. All right, our next speaker is, if I can get this to work. Our next speaker is Dr. Markus Rodehutscord from University of Hohenheim in Germany. And I'm not sure what, you can run it from back there?
Just go into the presentation mode.
Yeah, it's,
No, I don't know.
okay.
It worked a couple of minutes.
Yeah, it was working. I have some of my graduate students in the office, or in the audience. I want to assure them that I did check before this started that all the presentations were working, so sometimes technical difficulties arise in spite of your best efforts. So we're working on the technical problems. It'll take a minute or two. So the informal part of the Informal Nutrition Symposium, I guess, will allow you to renew acquaintances or make new ones.
Right. Hello, everybody. Thank you for fixing this. I mean, it worked when we tried it after lunch, but you never know, and perhaps this is something that happens when artificial intelligence is no longer under control. Anyhow, welcome. It's my pleasure to be here with you and to talk, as requested, about minimum phosphorus requirements of laying hens. And together with Vera Sommerfeld, who works as a postdoc in my group, we tried our best to squeeze out from what we have on data and also from more recent literature on that. Now, just to set the scene very briefly, when we talk about phosphorus, we have to keep in mind that we deal with a resource that is limited globally. And predictions are a bit different on how long we still will have them available or not, but for sure they will come to an end, and that makes phosphorus an important issue for becoming more sustainable in production. Related to that, of course, is what everybody knows probably, that this is a contributor to feeding costs, and that accumulation of phosphates in the excreta can be harmful to the environment when there is an emission into the surface body waters. And related to that, we have an increasing public concern about these developments, also leading to some legislative constraints to poultry production in some parts of the world. And that again has a feedback, of course, a feedback mechanism for production costs again. So it is for sure that we need to talk about costs, but costs is not all. When I started to get ready for this presentation and prepared it, I didn't expect that at the end of the day, the message that I can give will be relatively clear. So this is the number that I am planning to arrive at the end if the computer keeps collaborating, and I want to argue around that value in the next couple of minutes. So, but before we do that, let's take a moment to talk about terminology. So usually we talk about available phosphorus, and available phosphorus means that proportion of phosphate in the feed that can be utilized by the animal under marginal conditions of phosphorus supply. However, when you talk with people and ask what they mean by available phosphorus, you either get no answer or you get very different answers, what the understanding of available phosphorus is. And very often it is nothing else than non-phytate phosphorus contained in the feed. It is used in the same sense, which is not correct, because it assumes that phytate phosphorus is totally unavailable and that non-phytate phosphorus is available to the same extent, irrespective of the source. Both are not correct, but of course it's a kind of pragmatic improvement. So when digestibility is considered, we of course have the digestible phosphorus or the absorbable phosphorus. What you can find in literature when it comes to phosphorus retention, we have the retainable phosphorus or the utilizable phosphorus. We still have measurements going on relative bioavailability values. We do have increasingly ileal, or as we call it, presecal digestible phosphorus or ileal available phosphorus. And the problem is that all these terms do not mean the same. And the problem related to that is that this cacophonia of terminology is a disadvantage in arriving at precise recommendations on nutrient supply and also on feed tables with standardized values. Now, in the broiler sector, there is a fair, agreement, I think, that at least in this academic sector, that the digestible phosphorus is the method of choice for the future. There are committees around that published on that and gave a clear position. And we also had a symposium on digestible phosphorus a couple of years ago here at the PSA annual meeting. My personal opinion is that this should also be the case for laying hens, as soon as we have enough data available. For the moment, this is not the case, and non-phytate phosphorus probably is, for the laying hen, the best level to work on, and that is what I've used in my presentation. Now, when it comes to estimating the NPP requirement, we can do it with a simple, let's call it empirical model, as we have heard it before, very simple one, with a factorial approach. When you consider what the factors of the net requirement are, then of course we need to consider the egg. And the phosphorus content in the egg is relatively constant. You see the value here, approximately 1.8 milligrams of phosphorus contained in the whole egg per gram, and assuming 58 grams of egg mass per day lets us arrive at approximately 105 milligrams of phosphorus needed per day in the egg. And the second factor that we need to consider, important factor, are the inevitable phosphorus losses. So these losses that occur even when we have a very low phosphorus supply, and this value is from data of experiments that we did some years ago, where in a wide range of intake, phosphorus was varied and phosphorus excretion in laying hens measured. You can see the response in excretion here to this increasing intake, starting at very, very low levels, and the extrapolation to zero intake arrives at this 8.2 milligrams that I have used in this calculation. Data on ileal flow of phosphorus were also determined in that study. They indicate that the main regulation or adaptation to variable intake happened pre-cecally, but that is not relevant for the purpose of this presentation. Now, when we assume that usually the laying hen does not net retain any more phosphorus, then these are the two factors that need to be considered, and the net requirement accordingly then is approximately 190 milligrams per day. And now we need to consider a few variables, of course, and one is the NPP digestibility. In this example, I took the 75% as a relatively conservative value here. Of course, you can use other values if you have them. And the feed intake, very variable, as we have heard already. In this example is 107 grams per day, and when you use that values, then you arrive at this 2.3 grams of NPP required per kilogram of feed for the laying hen. Now, this is the simple factorial model, and we have also heard before that other approaches are also relevant, and this is an example for approaching requirement data by meta-analysis. I had Dr. Ahmadi from Tehran University visiting at that time in our department, and he's an expert in regression analysis and all these deep learning procedures and so on and so on. I mean, this data mining was not necessary in this case. As you can see, the data set was not very big, but that was what was available at the time, using diets that did not contain any intrinsic phytase, and they were compiled and analyzed by linear mixed models. In most of the experiments, the laying period that was considered here was longer than 12 weeks. Now, what this regression analysis showed was that the estimated NPP concentration in the feed that was needed for laying performance and egg production, as you can see here, was 2.2 grams per kilogram of feed, when no phytase was contained in the diet. And of course, with increments in phytase addition, the necessary concentration of NPP in the feed went down. Now, this was the outcome of that analysis at that time. That's already more than 10 years ago, and this couldn't consider any bone data or any eggshell quality data. So what I will do in the following is trying to summarize what we could find in the more recent literature on different levels of NPP in the feed, and start with performance traits here. And all the data that I included here in this slide, they refer to diets without any exogenous phytase. So let's start with a study that was conducted in Dr. Korver's lab here, where you can see the NPP levels in the feed reduced into phases to approximately 2 to 2.2 grams. The study went for 40 weeks, and there were no differences in feed intake, egg production, or egg per feed ratio. The group conducted another study with a focus on the early section of the laying period, again using two different phases, ending at a similar NPP level here as in the previous study. And as you can see, there were no differences in body weight, feed intake, egg per feed, and egg production. In this study that was published from China, the reduction was down to 1.7, and here egg production was reduced. In this study from Manitoba, reduction down to 1.5 in a 12-week study did not cause any effects on performance traits. And again, a study from Dr. Korver's lab looking at the later section of the laying phase, reduction down to either 2.1 or 1.6, did not cause any effect at 2.1 gram, but at 1.6. So, summing up, there is a clear indication when the NPP level is in the range of 1.7 or lower, then we have a problem, yes. But as long as data are in the range of 2 or 2.2, we do not have. When we then have a look at bone traits, we can consider similar studies, or most of the studies that I've shown before also measured bone traits. Perhaps we can do this a little bit faster. In this study here that we already started the previous slide with, there were no differences in tarsometatarsals and femur densities, mineral contents, and femur breaking strengths. The reduction here in this study, in the early section of the laying period, did not see differences in femur breaking strengths and bone ash, but there was a mildly lower cortical and trabecular and medullary bone mineral density and total bone mineral content in the tarsometatarsals, studied by computer tomography. Here there was a mild but significant reduction of some femur density traits and mineral content at 2.1, but stronger at 1.6 grams per kilogram. In the Manitoba study, there were no differences at all in the bone data that were studied. And this Chinese study specifically looked at keel bones. They identified what we have already seen this morning in Dr. Dunn's presentation, that there is an increasing problem with keel bone damages with progress in the laying period. And these problems were increased at the very low MPP content in the feed. So finally, eggshell quality traits. Apart from this one study here with the 1.6 grams per kilogram, there were no differences in any of the egg quality traits studied. So, I mean, this is what could be extracted from literature. We tried our best to review what was published. I am not sure if anybody is in the room who says, well, this and this should have been considered. I apologize if we couldn't find that. Please give me a hint after the presentation if more is available. But based on that, it is very clear that no more than 2.2 grams are needed in diets without exogenous phytase. So, and when we consider exogenous phytase now, for the next couple of minutes, then let me start with this relatively old study here, because it was the first study that I know who really looked at phytase effects on the substrate, on phytate. So they studied phytate degradation on the ileal level. And you can clearly see that with the supplementation of phytate, this was a 2-factorial design, phytase supplementation and calcium content of the feed. With the supplementation of phytase, the phytate degradation was clearly increased. It was on a lower level at the higher calcium content, but even at the high calcium content, there was a considerable phytate breakdown with the addition of phytase. And so there are not so many studies around that looked into phytate degradation in laying hens, but what is available shows that the principal responses to phytase in laying hens are similar to what we know from broilers. Maybe on a little lower level because of this very high calcium content, but the phytase principally works in the digestive tract as we know it from growing animals. More data are available that used phytase and measured whatever performance trait and bone data and so on and so on. And results from those studies are not very consistent. And I think that is simply a reason of the phosphorus level in the feed that was used. I would like to show you what I mean with this graph or graphs from a very recent study that we did with cystectomized laying hens. This was again a 2-factorial with 2 levels of MCP in the feed and 2 levels of phytase. This was at a very high phytase level here. And again, what you can see, phytate degradation increased up to 80% in the phytase supplemented diets. But when we then have a look what happened to phosphorus excretion, that was also measured here in this balance studies, and please have a look at the yellow bars here, then you can see that there was some reduction in phosphorus excretion when the feed did not contain MCP, but when MCP was contained, there was no reduction at all in phosphorus excretion, although phytate degradation was largely increased. And I mean, this is not a very big surprise. I mean, it just shows the enzyme does its work, but if the animal doesn't need the phosphate that is released, then it's excreted. What else should the bird do with it? So, phytate degradation in the digestive tract of laying hens is increased by phytase, but the phosphorus release from phytate can only be associated with performance and bone effects when the NPP level is not in excess. So this is a matter that may be considered in future experimental designs. So to sum up or to finish, I mean, we have heard about the necessity to more diverse and more complex models, and in this regard, of course, diversification of values in different periods of lay, especially in extended laying periods, may be of interest. specific environmental conditions, such as high ambient temperature, might be relevant. I remember 2 or 3 older studies that studied that and did not find any significant interaction between temperature and NPP requirement, but there are not many studies around. And strain differences perhaps also play a role, as we have seen, or as we have got indicated this morning by Dr. Dunn's presentation. This brings me to a short look at an interdisciplinary research unit that we currently have at the University of Hohenheim, because that involves working with 2 different commercial strains. So this is a relatively big project where hens are looked at in different periods of production and also in different stages of the laying period, with different levels of phosphorus and calcium and also inositol in the feed. And then a lot of samples, organs and tissues and so on are taken and used in different projects with very specific experimental and methodological approaches. And just to summarize that very briefly, what we know so far from the first funding period is that you can see the keywords here, that the brown strain is higher than the white strain, significantly higher in all these metabolites and nutrients measured in the digestive tract or in the tissues, the transporter expression, for example. Also, immunology traits are affected, and the strains responded also to different diets with a very specific jejunal transcription pattern, and differed in the expression of microRNAs and target genes of phosphorus and inositol metabolism. So far too early to conclude whether different requirements for the different strains can be concluded from that, but I hope that after the second funding period will be completed, we will be able to tell you more about that. So with the 2.2, I thank you and look for your comments.
Thank you very much, Markus. So if you were at the opening session this morning, you heard me talk a little bit about some last-minute changes and having to pivot a little bit. This next talk is a case where we had to pivot because neither of the authors were able to come to present. So I am going to play a recorded presentation. In the discussion session at the end, we'll have time for questions for our speakers if we're not able to get to them after their talks. And also we'll be communicating with the authors of this presentation by WhatsApp, so you can let us know your questions and we'll forward those questions on. So our next talk is Current and Future Considerations on the Determination of Amino Acid Digestibility Coefficients and Values by Paul Tillman and Bill Dozier.
Thank you for the introduction. When it comes to amino acid values for formulation, there are 3 main areas that need to be considered. Total amino acids, which can come from static tables or from dynamic values, such as those obtained from wet chemistry assays or near-infrared spectroscopy. The second area is digestibility coefficients. These also can come from static tables or also from dynamic values determined either in vivo with the apparent true or ill methodology, or in vitro, which will be some methods that we'll discuss in more detail here. And then thirdly is digestible amino acids, ultimately what we formulate diets on. And it's a calculation of total amino acids times the digestibility coefficient. Ideally, these should be implemented using a global equation within your software formulating diets. We will place emphasis on the total amino acids and the digestibility coefficients, primarily in this presentation. In doing so, 2 matrix values were created based on some assays on soybean meal, which have been conducted using precision-fed susceptimized roosters at the University of Georgia. There were 12 soybean meals tested, and the HPLC assay was used to determine the total amino acids in both the feed as well as the feces. And then the digestible amino acids were calculated based on the determined digestibility coefficient. So an ingredient was created with this name, and it has a D here in the middle, indicating that the values were determined for the digestibility coefficient. And a safety margin was applied, which was based on mean minus half of that standard deviation. And then a second soybean meal was created with a P, meaning that these values were predicted for the digestibility coefficient. This was used in NIR data, and I'll go into more detail on this methodology. And again, a safety margin was applied. So this is the first soybean meal that was created, the one that was determined. Here are the total amino acids based on the HPLC assay and the adjusted with the safety margin digestibility coefficients, and then the calculated digestible amino acid values. A basic corn soybean meal diet was formulated using 5 amino acids: methionine, lysine, threonine, valine, and isoleucine. And these were used in order to meet the ideal amino acid ratios that were set as minimum constraints. When we look at where the amino acids come from in the diet, corn, for example, provided about 25% of the nitrogen, but 70% of the energy. Soybean meal, on the other hand, provided 72% of the nitrogen, or the amino acids, if you will, and only 23.7% of the energy. If we look at where the amino acids come from, the value at the top is the least amount that came from either corn or soybean meal. In this case, for soybean meal, the least amino acid that was provided from soybean meal was digestible sulfur amino acid. And then the values increase as we go around the pie chart here to the highest level that was provided. You can see this ranges from greater than 65% for threonine all the way up to 86% for tryptophan. If we also factor in the balance of where the nitrogen and the energy comes from, the added amino acids from these 5 amino acids that were utilized provides another 2.9% of the nitrogen and the added fat of 5.2% of the energy. The point here is that focus in your matrix value should be based on energy for corn and nitrogen and amino acids for soybean meal. A paper was published in 2019 based on a presentation given at these meetings, the Informal Nutrition Conference, back in 2016, which looked at the nutrient values for added or commercial amino acids. And the first step that was utilized was just taking the molecular formula and determining the percent nitrogen, and then exploding that out to crude protein. The normal factor of 6.25 was used, which is based on a 16% nitrogen in that particular amino acid. And you can see that is not always the case. Arginine here has 32% nitrogen. Some of these other ones have very low levels of nitrogen. So we use 6.25, but it's not exactly correct. These type of values were also reported in NRC from 1994, about 25 years earlier. But it should be pointed out that this is just on pure amino acids. And so to utilize these, we need to adjust those based on the potency of the commercial product forms we have. Similarly, energy values were also shown in the paper from 2019. 4 different sources were used, one from NRC in 1994, and a mean value was calculated with the standard deviation here to allow for some safety margin to be applied if you so wanted to do so. Again, these are on pure amino acids, need to be adjusted for commercial, and similar values as shown here were reported in the NRC from 1994. So there are a variety of sources out there for getting information on total amino acids, digestibility coefficients, or digestible amino acids. These values can be static from tables or dynamic or predicted values. 3 of these publications shown here only provide static amino acid values, and we'll talk a little bit more about some of the predictions. For example, NRC in 1994 had 2 prediction equations The first one here was based strictly on crude protein, and it would use an intercept and a coefficient to determine some of these key amino acids. Valine and isoleucine was not included in this analysis. You can see here, this is on a 47.8% protein, gave about a 2.93% digestible lysine. The second equation in NRC used more of an approximate analysis approach, so included other nutrients in the equations. For a lysine, for example, there was still an intercept and a coefficient for protein, but it also added ash. Using the same crude protein as above, it predicted lysine to be 3.19%. There's about a 9% difference here between these two methodologies using the same crude protein value. In 2010, a paper was published that looked at 500 soybean meal samples based on true total amino acids for a 6-year period, 2002 to 2008, from a Genomoto database. And it was shown that just by using crude protein in the formula, it's very difficult to accurately predict a given amino acid. You can see the R squares here that run quite low on this prediction when just having the coefficient for crude protein along with an intercept. RIRDC is a publication out of Australia. They looked at 15 different soybean meal samples, and they're ranked here based on protein from 44.8 up to about 50%. And I would like to point out here that if we look at the lowest protein, it doesn't always mean that it gives that the lowest particular amino acid value. Similarly, the highest protein is not always in that particular soybean meal sample. So what this is telling us is that 100% linearity of crude protein and total amino acid value should not be assumed. This publication also had some prediction equations. There were 3 different sets. The first one uses crude protein with a coefficient along with an intercept to predict amino acids, as shown here. Then there's one that uses the crude protein with the intercept and coefficient to predict digestible amino acids. And then there's one that uses a digestible crude protein, which is calculated from the true or total crude protein value shown here. And it also predicts apparent ileal digestible amino acids. So this uses intercepts and coefficients like many of the equations do. And this assures a variable relationship between the amino acids as these prediction equations are utilized. Another area that is oftentimes used in feed formulation is amino acid factoring. This is where you basically set up a factor based on crude protein to change your total amino acid levels accordingly. And this just does so proportionally. So if, for example, if crude protein goes down from 48 to 47, that's a factor of about 0.98. And that 0.98 factor gets applied to every amino acid. Similarly, if it goes up, it's a factor here from 47 to 48 of 1.02. And again, that gets applied to every amino acid. So if a global equation is used to calculate digestible amino acids in your formulation software, then each digestible amino acid will automatically adjust with these factors on the total amino acids. But I would caution people to use this. And if they do this, I would say first, use a very small increment versus the actual CP change when factoring. So instead of doing a full percentage point, I would recommend a smaller change initially and with factoring, and then secondarily set the crude protein based on the assay, but do not factor any further than that. So I say use factoring sparingly or not at all. Really, we need to be relying on dynamic total amino acid assays or NIR predictions instead. Another publication from Brazil in 2017 provides both static values along with standardized ileal digestibility coefficients and a calculation on the standardized ileal digestible amino acid. They also have equations in there, an equation for predicting total amino acids based on crude protein, but it's a little different approach. They take crude protein and run it through an equation to come up with an amino acid sum value. And then that amino acid sum value is put against percentage of amino acids in the sum to calculate what the lysine or methionine or threonine level should be. Because of this, the predicted amino acid values do change linearly with crude protein, but remain constant to each other because a constant factor is applied. Another source of information is from Evonik AminoDat. This is 4.0 version from 2010. They had prediction equations in that particular version. Since then, they have newer versions. I think they're up to 6.1 now. And here's a table from the AminoDat 5.0 in 2016 that also reported average amino acid values on a total amino acid basis, along with some descriptive statistics. There's two dynamic methods for amino acid analysis that I'll point out here. One is wet chemistry, considered the gold standard for determining total amino acids based on HPLC. It's also required to generate the NIR total amino acid prediction equations. And secondarily is NIR. It's used in agriculture industry. We can use it for approximate analysis, total amino acids, digestibility coefficients, digestible amino acids, along with other nutrients as well. But it's still not fully accessible or utilized by the poultry industry to the extent that it could be. Access by smaller companies, for example, is often limited as to what they actually can acquire. But good correlation exists between the lab assays, the in vitro lab assays like HPLC on total lysine, and the predicted total lysine from NIR, 2.82 in these 41 samples versus 2.8. Other amino acids also show similar predictability. And it can also be used for predicting digestibility coefficients. So this is 27 samples, and again, the digestibility determined in vivo is 88.3, but predicted was 87.9. So again, good correlation between the prediction and the actual. Another method that can be considered is the immobilized digestibility enzyme assay idea from Novus. And it's an enzymatic assay. And relationships between the ideal value in soybean meal and the in vivo lysine digestibility value have also been shown to be highly correlated with the R-square here of 87. I had access to two different big databases based on soybean meal assays. And the first one was based on wet chemistry from Ajinomoto using HPLC that gave me dry matter, crude protein, and total amino acids from a 6-year period and across about 2,400 samples. Second one was using NIR from Adicio and their precision nutrition evaluation program, which combines both in vitro along with in vivo digestibilities for a precise characterization of raw materials. It was run for a 5-year period across about 2,500 samples. Here's the descriptive statistics from the Ajinomoto database. Again, 2,030 samples were used here, showed an average crude protein around 47% and a total lysine of 2.87. If we look at that data plotted with crude protein against total lysine, the results by year look like this. The slopes are not exactly the same across each year, and the predictability gives us very low R-squares, as can be seen here. And obviously, the intercepts and the coefficients are different for each year. So what this means that we might need to know this for every year. So this really might require a more dynamic approach than just using one particular equation. Similar results for total amino acids using the prediction from the P&E program gives us a mean crude protein of 46.5% and a total lysine of 2.92%. Not that different from the Ajinomoto data. And again, plotted across year, we can see a little bigger difference here in the slopes. But again, the R-square values here are not very high, saying that using a single nutrient like crude protein to predict total lysine is not very accurate. And again, so we may need a more dynamic approach in trying to come up with some of this. The P&E value can also, program can also predict digestibility coefficients for each individual amino acid. This is shown for soybean meal. So the values here on mean are pretty standard type numbers, or well within the realm of what we would expect to have. And the sample size was quite large across this database. I will point out that the digestibility coefficient for sulfur amino acids, methionine and cysteine, should be based on a weighted average. So if we take the digestible sulfur divided by the total sulfur, we should get the accurate digestibility coefficient for the sum of the two sulfur amino acids. A couple of years ago at 2012 Poultry Nutrition and Milling Seminar at the Alabama Grain and Feed Association meeting, I presented this information where we looked at predicting digestibility coefficients for meat and bone meal using total amino acids in the equation. So we use stepwise regression here to determine which amino acid, along with crude protein, might be significant in a model to predict the digestibility coefficient of a given amino acid. In this case, lysine, and it used these particular amino acids along with crude protein. If we compare the predicted value, 81.4, versus the actual determined value when the soybean meal was fed through roosters, you can see they correlate quite well with a very high R-square, similar to what we see across these other amino acids. We got very good R-squares and good predictability. If we compare those, the predicted versus the actual determined value, you can see there's very good correlation across here. If we use these values against the total amino acid of the average soybean meal fed, we come up with these digestible amino acids, which differ very little on an absolute basis or on a percentage basis. So this told us that using predicted digestibility coefficients from total amino acids was possible for meat and bone meal. And it raises the question, could this approach also be an option for predicting digestibility coefficient for soybean meal? So we looked at that using the NIR information from P&E, DICIO, that has this information. And we were able to show that by using dry matter, key amino acids, and crude protein, that we could indeed predict the digestibility coefficient for lysine. This graph shows the order of significance or the impact that each of these has. Dry matter has the greatest impact on predicting the coefficient for lysine, followed by phenylalanine. And interestingly enough, lysine has the least impact. All of these values were highly significant to the model. You can see that here. And the model was highly significant and had a very high R-square. So it's telling us, yes, we can use total amino acids to predict digestibility coefficients for different amino acids, in this case lysine, in soybean meal. This one used 10 variable inputs. Here are what the other amino acids look like and the inputs that they required. One thing that I'll just point out is that all of them use dry matter, all of them use leucine, and all of them use threonine. And some of the coefficients are negative, some are positive, but they all were significant to the model and gave significant and high R-square predictabilities. This is the result from taking the total amino acids from the Ajinomoto database and putting against the prediction equations that were just shown with the coefficients in the prior slide. And then these are the predicted values across those 2,030 Ajinomoto samples. And again, they fall well within the realm of what we might expect for these different amino acids. The standard deviations shown here could be used to apply a safety margin, as I've mentioned earlier, and that's oftentimes done. I recommend putting the safety margin on the coefficients, not on the total amino acid that you need for assay reasons. So here's the formula utilizing the same soybean meal that I showed in the determined equation, but now we're using the digestibility coefficients that are predicted with an applied safety margin, and then the resulting digestible amino acid. Again, a corn soybean meal diet using 5 amino acids was generated using ratios that were able to fall down to the supplemented amino acid that was used. And if we look at the layout of this and how it fits relative to the first diet based on predicted, again, we see that soybean meal is the main source of our amino acids. 36% of our sulfurs are coming from soy, then 61% of valine, 62% of threonine, all the way up to 84% of our tryptophan. And so soy is providing 71% of the nitrogen or the crude protein or the amino acids in this particular formula. And again, the added amino acids are bringing some nitrogen and some energy. So these aren't great amounts, but still should be utilized in your formulation matrix for your added amino acids. If we compare the two, they both had the same total amino acid for the soybean meal used. Here are the coefficients used in the determined through the precision-fed cystectomized rooster. And here's the predicted values using the total amino acids here from the assay put against the prediction equations generated from the NAR data. And then here's the digestible amino acids. There are some differences here, which we attribute to the method that was utilized for the most part. The predicted values from the NIR used a modified precision-fed cystectomized rooster assay, which is more based on a complete feed rather than feeding just a single ingredient. Here's the formula comparison between the two, the determined and the predicted. And you can see there's not a lot of difference between the ones out here. They were all formulated to the same amino acid ratios and the target amino acids. And if you look at the difference here, corn only different by 0.4 percentage points. Soybean meal only different by 0.5% percentage points. Oil only different by 0.1 percentage point, and amino acids also not showing a lot of difference. So by comparing the determined and the predicted, we were able to show fairly similar formulas were generated from using those particular values. So in conclusion, we would recommend using a dynamic total amino acid assay, either from wet chemistry, which is the gold standard, or predicted from NIR. Digestibility coefficients, either use in vivo values, which are gold standard, or an in vitro methodology like an enzymatic assay, NIR, or what was proposed here, an equation predicted from total amino acids. And then again, the dynamic value should be calculated from these two, total amino acid times the digestibility coefficient. I recommend using that as a whole number so it's not confused with the total or digestible amino acid value. And I recommend using that within your formulation software so it's automatically generated on any change in either your total or your digestibility coefficient. So I'd like to wrap up and say thank you to Ajinomoto and Adicio for access to the databases that we were used in this particular paper, and then Nutritional Statistics LLC for assistance in analyzing a lot of this information. Thank you.
As I said, we'll have an opportunity for questions at the end of our session. Our final presentation before the break is from Rob Gous from the University of Kwazulu, Natal in South Africa. And Rob will be speaking on optimization, formulating to meet the objectives of the business.
Good afternoon, everybody. It's a great pleasure for me to be here, and I'd like to thank Rosalina and Doug and the committee for thinking it worthwhile bringing me all the way from South Africa to talk to you this afternoon. My presentation is going to be about decision making. This is something that we do every day. We have lots of alternatives, and we have to choose between those alternatives. If you think about poultry producers, they have to make decisions about which breed to use, which housing system to use, what temperature to use every day of the growing period, and many other decisions that keep them occupied. When it comes to, let me try that one. When it comes to poultry nutritionists, they have to make decisions about the minimum levels or the lower bounds that they put into their feed formulation programs. And they have to make these decisions based on the type of curves that you see there, the dose-response curve. This is a simplified version of a dose-response curve, and the decision that they have to make is what is that for each amino acid in turn, what is the level that they're going to choose to have as the lower bound. Now, the conclusion that I can come to when I look at a curve like that, because of the curvature of that response, you need more information than is given there in order to make the decision about the amount of lysine or methionine or whatever to put into the feed. And I will talk about that a little bit later. But there are two interesting aspects to these dose-response curves. So the first is what determines the shape of that response curve. And I will spend a little bit of time talking about that, because I think it's really important to understand that in order to determine, before you make a decision about what level of the dose is required. And the other interesting aspect is how should the response be interpreted. And I'm going to draw on a lecture given by my mentor, Trevor Morris, to point that out to you. And I think it's really important, especially for the younger people in the audience, to hear that particular aspect of this talk. So, to talk about what determines the shape of the response curve, remember that this is made up of a number of individual responses, and the individual responses all look like this. This is for amino acids. There's the maintenance requirement has to be met before any, I'm taking egg production here to start with, because with laying hens being in a relatively static phase, you don't have to take changes into account when you measuring these responses. So in a laying hen, the maintenance requirement for an amino acid has to be met before there's any response, and then that response is linear up to the point where the genetic potential is reached, and then it doesn't matter how much more you feed that hen, you won't get any further response from her. And the point where that line breaks, that is the requirement. That's the definition of a requirement. Now, it can really only be applied to an individual, because in a population, you have large numbers of birds, all with different maintenance requirements and all with different potential egg outputs. And the maintenance requirements form a normal distribution, as do the potential egg outputs. And in the case of laying hens, there's no correlation between the maintenance requirement and egg output. So within a strain, that is. So you can get some small birds that lay very well and not very well, some large birds that lay well or not very well. No correlation between those two, and that influences the shape of the response curve. The fact that there's no correlation between the two the maintenance and egg output, will influence the shape of that response curve. Remember that this is a population response, and please note the degree of curvature of that response, because the next is that I'm going to talk about body weight, and in that case there are also large numbers within a population of different maintenance requirements, also made up of a normal distribution. But in this case, within a population and at a given time, there is a negative correlation between, it is a positive correlation between maintenance and the potential weight gain. So the smallest birds have the lowest potential weight gain on that day, at that particular time. This is a population response at a time, and the effect of that is to smooth out the curvature, and it's much more smoothed out than in the case of the laying hen, where there's no correlation between those two variables. So it's a more gentle response. Now, the other thing about broilers, apart from the fact that within a population at a time you get this variation, each bird over time is also changing in its maintenance and its growth potential. So a single bird over time is also going to have a positive relationship between maintenance and growth. And these two combine, when you're modeling, when you're feeding birds, you have this combination that you have different birds in the population and they're all growing at the same time. And the shape of that response curve changes quite considerably. If you keep the birds going for a long period of time, I meant to point this out, the maintenance requirement, as it keeps going up, you'll get a maximum growth rate on a day, and then it starts declining as the growth rate declines. So you can alter the shape of this curve any way you like, really, by increasing the length of the growing period. So the fact that there's the response of a population is a curve. There's no obvious requirement as such. That's why I said the requirement should be applied to an individual and not to a population. So that's the one thing about shaping the shape of the response curve. The other is how this can be interpreted. And as I say, this is Trevor Morris gave this presentation, and I was so impressed with this because I felt that it was really important to understand how differently some people will interpret a response like this. So there's a typical type of response curve, 5 levels, which is about the minimum you should use in a response experiment. And the first, the question posed is, how many units of that dose should we use as the requirement? So the first way of analyzing it is to use Duncan's multiple range test. Now, I hasten to add, you should never ever use Duncan's multiple range test to analyze a response experiment, and anybody who does should never pass their degree. But the point is that if you do use this method and you look at significant differences between treatments, there might be a significant difference between the first and the second dose, but then after there are no significant difference. So you can assume that 2 doses is the requirement. The next way is to use a broken stick method, and if you do that, 3 doses is the requirement. You can fit a second-order pollinator, a curvilinear regression and come to the conclusion that 4 doses is gives the maximum. Or you can, like some farmers do, they say, well, we want the maximum, please. So you would go to 5 doses as the requirement. And then, you can even be better than that, you can fit an exponential, and that goes on forever. So you have to then stop it at some point. So you say, well, let's take 90% of that requirement as the potential, and that would require 6 doses to get to that. So the conclusion from that is that choosing a requirement using statistics is really unhelpful. So we have to have some other information in order to do that. And really the information that we need to make it useful to a farmer who's looking for profit out of the operation is to look at the economics of it. An economic optimum is so much better than a statistical optimum. And the point there is that in order to determine the economic optimum, you have to take into account the costs of the nutrient that's being used and the revenue for the output. And the additional information that I was talking about earlier has nothing to do with the growth rate, because we measure that very successfully. What we don't measure successfully and what we aren't able to predict successfully is food intake. And unfortunately, a lot of people just believe that food intake is regulated by the energy content of the feed. So the mantra is that birds eat to satisfy an energy requirement. And if that were the case, we wouldn't really need to take feed intake into account in this exercise. But I have news for you, and feed intake is hugely dependent on the protein content of the feed. It is altered considerably by the protein content. It's not just energy that is causes changes in food intake. Protein does as well. And the reason for this is that birds try and eat as much as they can of a given food to get to grow at their potential. And if you drop the protein level, they will try and eat more of that feed. They're not successful in doing that, but they try. And that's why the food intake increases as you drop as you drop the protein level. This goes on for a while, but they become increasingly unsuccessful at managing to consume sufficient food, and eventually the wheels fall off completely and food intake starts dropping. So that pattern, which was done by Dave Burnham, some of you know Dave, it was done many years ago, is a very good illustration that we need to take account of food intake. So let's just talk about the conventional approach that's used by nutritionists to work out a requirement. They believe that birds have a requirement, and they formulate to meet that requirement at least cost. And some people who are brave enough will adjust that requirement depending on the amount that they are allowed to by their bosses to feed either more or less of that. But generally, the amount that they use is static, and they won't change that from one period to the next. That approach ignores feeding costs. Obviously, it's related entirely to the cost of the feed, but the feeding cost is ignored, as is the value of the output. But those are what constitute what the farmer is wanting to do. He's wanting to make a profit, and in order to make a profit, you have to take the money into account. So this leads on to optimization, and optimization is a means of determining the level of nutrients that will maximize or minimize a given objective function. Now the objective function can be anything that can be measured, basically, but generally it would be something that includes expenditure and income. So margin over feed cost would be a very good example of an objective function, but it could be cost per kilogram of gain. So you would want to maximize margin over feed cost, or you would want to minimize cost per kilogram gain. So in order to do that, you would need to determine the level of nutrients that will maximize, the information required includes the cost of the feed, which every nutritionist knows very well, because that's what they are interested in doing, minimizing that. It requires information about the feed intake. It requires information about how the bird is going to be sold, whether it's going to be sold live or dressed or further processed, and the value of whatever that product is that is going to be sold. So you need, if you're selling further processed birds, you need to know the value of the product and the weight of the product that is to be sold. So one way of doing this, of finding out what the optimum economic level is, or to maximize margin over feed cost, would be to do an experiment. And I'm going to give you an example of an experiment that was done by a student in Brazil. And this is a very good, it's a good example of how you can go about finding out, using different objective functions to find out the way to feed birds most economically. So you would take, in this case, a three-phase feeding program. The normal feeding program that you would use on the farm. You would use levels of above and below the recommendations, whatever those recommendations are, whether they're Aviagen or COB, or in the case of the student in Brazil, the Rostanio recommendations. And you would choose levels higher and lower than that to give you the 5 or 6 different levels of protein in each phase. So you have to specify the lysine level, the amino acid levels associated with that, and then keep all of those in the same ratio over the 3 phases. And we use a balanced protein in that case, so I refer to 100% as the recommended level and go up or below that. So the measurements that you must take are feed intake, and measure that as accurately as possible. Don't assume that it's going to be the same in each case, and the live dressed or processed weights at harvest. And the results, this is a bit complicated, I have it in graphic form in a moment, but just to show you that the Rostanio values are not the same as the COB and not the same as the Aviagen values. So the Rostanio 100% is 110% for COB and 106% for Aviagen. That's taking an average over the 3 periods. And you'll see in this case where we've separated the males and females, and I've given you examples at day 42 and day 56, that at day 42, if you're sending the birds live, it doesn't pay to go to what Rostanio regarded as being the requirement. The requirement would be 85% of that for both males and females, and at both of those ages. Those numbers are given to you in red, so you can see them more easily. If you sell the birds dressed, for the males, it's worth going to a higher protein level, but females still at the lower level. That gives you the maximum margin over feed cost, and that applies at both 42 and 56 days. But if you sell birds further processed, you go to the highest level possible, because you're going to get more bang for your bucks if you do that. Graphing it, you can see that very, very clearly that the margin over feed cost is lowest for whole birds, and consequently you don't want to feed very high levels of the protein at that stage. This is for males at 42 days, just given one example for males at 42. The next one is for females at 56 days, just to show you the contrast. And because I've drawn graphs, it's more possible to be more specific about the level that is the optimal. So it's around about 85% for the males at 42 days. If they're whole birds, it's about 94% for dressed birds, and about 108% for further processed birds. Then if for the females at 56 days, it's less. It's only just over 70% of Restagno's values for whole birds. I mean, it's a huge difference from what was recommended to the maximum margin over feed cost. For dressed birds, just less than 90, and for whole further processed, just less than what Rostagno recommended. If I just toggle between those two, just to show you the difference in the shape of those curves, you'll notice it shifts, showing that males and females differ in their response to protein. What happens if the price of protein goes up? When we did this exercise, we said, well, let's really go big. Let's increase it by 25%. Well, it's gone up hugely more than that. So we could have done this exercise maybe at 50% increase, but we've stuck to 25% for this exercise. And you'll notice from the table there that as we dropped the price and we increased the price. If you drop the price of protein-containing ingredients, so this was soya and all the synthetic amino acids that went into the feed, it was worthwhile feeding more, a higher protein if the price came down. And in all cases, that applied, but still it was the live birds had the lowest protein level, and the further processed birds had the highest protein level. And if you go at the bottom of the table, where the price of feed of protein went up by 25%, you can see that it doesn't pay to go to the same level as the base. So this is a dynamic approach. As the prices change, it's worthwhile taking that into account so that your operation can maximize profit. I talked a little bit about objective functions, and there are a list of 4 of them there. The first 2 include finances, the other 2 are of interest, because some people want to increase breast meat yield, thinking that this is going to bring in the maximum revenue, but in fact it's worthwhile taking the price and the value of that into account as well, not just maximizing for the sake of maximizing. And then in the Netherlands, for example, they might say they want to minimize nitrogen excretions, and that might be an objective function as well. So I wanted to take those into account to show you what the effects are of choosing different objective functions. So the first column after the description is the base. In the starter, it was 12.8. This is the amount of lysine. This is used as the basis for the protein. 12.8 lysine in the starter, 11.8 in the grower, and 10 grams per kilogram in the finisher. I think these are the Aviagen recommendations, if I remember. And below that, you'll see what the this was using our broiler optimizer. You can see what the the values, the performance variables are when the birds are given 12.8, 11.8, and 10 grams per kilogram of lysine. So if you want then to maximize margin over feed cost, you would expect the optimizer to find a better solution. And indeed, if you look at margin over feed cost near the bottom of the table, it increased from 602 to 711 cents per bird. And in order to do that, the lysine level in the starter went up, but in the grower and the finisher, it went down. So that's a way of increasing the margin over feed cost and not really badly influencing anything else. The feed conversion ratio went up by 3 points, and the bean counters who want to minimize feed conversion ratio would be horrified by that, but in fact you're making more profit. So let's see what happens if you want to minimize feed conversion ratio. That's the next column along, and indeed you can drop the feed conversion ratio by 3 points, 1.58 to 1.55. And if you look at what effect that has on the margin over feed cost, it drops from 602 down to 588, and the farmer doesn't make any money, or makes far less money. So the opportunity cost is very high of choosing feed conversion ratio and minimizing that. Finally, the minimizing nitrogen excretion, that's possible. Dropped from 96 down to 83 grams per bird, and that was achieved by dropping the protein, the lysine, in each of the feeds in the feeding program. And the margin over feed cost, interestingly, was still higher than the base, but lower than you could get by maximizing margin over feed cost specifically. So depending on the objective function, you can achieve what you're setting out to, but it has repercussions on other variables, and you need to really be aware of those repercussions. So those tables illustrate the effects of different sexes or genotypes, and this is because different sexes, the two sexes and different genotypes have different potential growth. They also respond in feed intake to protein in different ways. The yield of parts differs between males and females, and certainly the cox composition is different. And all of those have to be taken into account when you are optimizing. It also showed different, the effects of different end products. So selling the birds live, dressed, or further processed will influence the optimum way of feeding them. I showed the differences in feed protein prices and the effect of that on the optimum, and the effect of different objective functions. So all of these can be accounted for using simulation models, but the simulation model has to be able to predict food intake, and many models don't do that. You have to be able to predict food intake before you can use a model to optimize the performance. So the conclusions are that the conventional approach of using a fixed set of amino acid requirements is outdated. I hesitate to say you should never do it, but it is certainly outdated. The decisions, nutritional decisions, need to be made on the basis of the objectives of the business. And the objectives of the business are, the main objective of the business is to make a profit. It's not to minimize the cost of feed. So the objective is to maximize profit of the enterprise through the process of optimization, and those decisions have to be made quickly if the company is to benefit from that process. The best way of benefiting is to have access to a model that does that. I'm not suggesting that you should, but that is the best way of doing it. The alternative is that you do an experiment like I've described, and you make use of the data from that experiment until such time as the genotype changes or your housing or whatever changes. And then you should redo that experiment in order to get more updated values that you can use in the way that I've shown you there now. Thank you. That's what I have to say.
All right, thank you. We do actually have one more thing on our program before the break, so I'd encourage you to take a moment. Todd Applegate is going to say a few words and make a couple of presentations.
Good afternoon, everybody. How y'all doing? Are you ready?
Do you want a microphone?
I got one.
There you go. You got to turn it on.
I don't know if it's on. Is it on? It's not on. We'll try again. How do I turn this on? There we go. Okay, this is on now, I believe. So, this is my favorite part of the program. And I think it's one of the very few places that we begin recognizing what folks contribute to others, right? Oftentimes we're giving awards more for what people are doing individually. In this case, I think we, as one of our wonderful things that we do within the Poultry Science Association really is networking and giving back to others, recognizing that we really want to invest in future generations. I'm in charge. Okay, thank you, Doug. So as we look to mentorship, and maybe it's the age I'm getting to is really placing more value on this and how we really need to begin focusing more of how we give back to others, is really, what is a mentor, right? If we look back to that wonderful resource of Wikipedia and how they define it as really as an experienced and trusted advisor, one that understands their role is to be engaged, authentic, and tuned to the needs of many. So I think for me, especially for the graduate students in the room, often we think of those mentors as singularly your major professor, right? But I challenge you to think more broadly in what you need to grow in professional and personal development. Oftentimes, you really need to think of that in its plurality. And so today we're recognizing 3 individuals, and I'd ask you to please come up and join us up here as we really celebrate what you have done currently and throughout your careers, really in contributing and giving back to others. So the 3 that we're recognizing today, first is Ryan Dilger from the University of Illinois. Next, Dr. Elizabeth Centine from Jeffo and ISI Institute, yes? Congratulations. And last, Dr. Rob Gous from Kwazulu, Natal in South Africa. Congratulations. So thank you to each of you for what you have given in terms of time, resources, just in helping others through their journey and their career path. So thank you so much for your time and effort. If you all have a chance over the break, we'll reconvene Doug at 3:30. So over the break, please congratulate these folks for all their time and contributions.